Hi, everyone, and welcome to the National Stock Assessment Science Seminar. My name is Bailey. I coordinate this monthly seminar series that highlights interesting advances and topics in stock assessment science. We're excited to welcome back Dr. Steve Saul today. Great to have you with us, Steve. Steve's research applies an interdisciplinary systems based approach to understanding marine resource dynamics, the ways that humans use these resources, and the feedback between humans and the natural system. He has worked closely with a wide range of partners, including international and domestic government agencies, intergovernmental organizations, nonprofits, private companies, and coastal communities, developing scientific tools to help guide policy. And in today's seminar, he will walk us through a workflow that brings together information limited fisheries methods and sensitivity analysis in a new way. And without further ado, I'll turn it over to Steve. Thanks again for joining us.
Thank you so much, Bai and Cassandra, and thanks to all of you for having me. So today I'm going to talk a little bit about some research I've been involved in since about 2018, working on combining data limited assessment techniques in a novel way to evaluate the status of Indonesia's demersal finfish populations, and in a way that allows fishery managers to be presented with a range or a menu of different possible trade-offs across the biological, economic, and sort of nutritional areas for fisheries. And so, as I mentioned, the main driver behind this work was to conduct a trade-off analysis that estimates stock status as you would typically during a fishery stock assessment, does some forecasting and can estimate things like rebuilding times, but also links uh, the sort of forecasting work and such with an economic model to estimate profit, and with a nutritional model to calculate the sort of nutritional um, composition of the catch that you would get under different management scenarios, with the idea that these can be used via decision theory by managers to develop or identify best policies. And so it's a model ensemble approach, as well as a full sensitivity analysis around a variety of uncertainties that are present in the catch, life history, recruitment, and other aspects of this work, which I'll describe shortly. And the goal is to estimate biological, economic, and nutritional outcomes across a variety of different fishing mortality scenarios. And why, of course, I'm biased, but why I think this work is interesting and novel is the way that I've sort of combined approaches and the ability to then reconstruct population demographics, and to forecast and estimate reference points in a data limited under data limited conditions. So the data used in the analysis, it was collected from a cooperative program that started in 2016 in Indonesia through a partnership between the Nature Conservancy, the University of Rhode Island, and the national government within Indonesia. And this data collection program has a sub-sample of the fishers who participate in the demersal uh, snapper and grouper fishery, contribute their data, so both length data by, as you can see in the pictures, by taking photographs of their catch on measuring boards. And there's also a logbook style data collection program where fishers that participate in the program have to complete or fill out a logbook style report at the end of each of their fishing trips. Participating fishers are also have a small GPS device that they carry with them, which shares their location with the database essentially throughout their fishing trip, and so we have a sense of where they're fishing and where their catch is coming from. And so to date, about 10 million fish lengths have been measured across the nation, across of Indonesia. And this work will assess 395 distinct, what we'll call stocks. And these stocks comprise of 43 different species across 11 of the fisheries management regions, which are the on the bottom right figure, the sort of regions outlined by the yellow lines, and where you see three-digit numerical codes in the map there. And not all species occur in every region, which is why there are 395 stocks that are being assessed. I'll go through kind of an overview of the workflow, and then I'll dive into a bit more detail on different aspects of the workflow. And so, first, we acquired the landings and fishing effort data from those trips that are providing logbook style data for those fishers that are participating in the data collection program. And we, because not all vessels are sampled, we had to extrapolate up our landings estimates to the entire fleet. And so a comprehensive fleet survey has been done twice so far that has looked at all of the vessels that do participate in the demersal fishing operations across Indonesia, and there are a little over 10,000 of those vessels. And using sort of catch rate information from the logbook style data, we use that in combination with knowledge about from stakeholders about average days out fishing and such to scale up and estimate the total removals or landings by species coming from this fishery since this data was collected starting in 2016, which I'm calling the sort of modern period. We also looked at historical catches from the sea around us data as one possible scenario to try and improve estimates of biomass. As we all know, having a longer time series can help improve those estimates. The catch information is used together with a catch MSY type model to develop an estimate of current biomass. And there are a number of different sensitivity tests around landings uncertainty and depletion assumptions, which I'll talk about in a few moments, that go into that work. You'll notice also that local knowledge and stakeholder input was sort of an important part of this entire process since 2018. And we've iterated on multiple parts of this workflow to try and improve the assessment and its outcomes. Then 5 different life history parameter sets were used to sensitivity test around life history variability, since there are not really empirical studies or otolith data collections or anything like that for these fisheries. And then the length data and the life history information together with the length data was used in 5 different estimation models to estimate current fishing mortality. So 5 different data limited estimation algorithms to calculate fishing mortality and develop an estimate of current F essentially. And then that information, the biomass estimate is then combined with fishing effort estimate and our life history parameters to then move to the catch at age or the numbers at age world, I should say, and I'll explain in more detail how this is done shortly. And then a life table type approach is used with the vector of numbers at age to forecast the population dynamics forward in time. The estimates of expected catch from these forecasts are used together with the upside economic model to calculate profit and catch trade-offs when managing at different targets, and I'll talk more about that as well. And then the NutriCast model is used to calculate nutritional trade-offs, again, depending on your portfolio of species that are being caught and what the sort of landings are for those species under different management scenarios. Last, results are presented to government scientists and stakeholders There's been a whole lot of really important stakeholder and management engagement. We've obtained feedback from them, and then gone back and made changes to this workflow and reran the workflow, represented the updated work, gotten feedback, and iterated around this workflow a few times, until we've gotten to this point now where folks are generally happy with the workflow. And the next step will be to move forward with using it to discuss policy decision making. So for landings, the sort of modern catch is from 2016 to 2023. That the data we used was up to 2023 in the assessment, and is extrapolated to a fleet survey, as I mentioned, from logbook samples from the handful of vessels that are participating in the data collection program. That's done using average catch rate per vessel capacity and the average number of days fished, based on vessel type, vessel size, and the fishing gear that each vessel predominantly uses. Historical catches between 1950 and 2020 are extrapolated from the sea around us data, and then we used and so that information, together with information on depletion, is needed for the catch MSY algorithm. And so we don't have estimates or direct knowledge of depletion from this fishery. So as a proxy, we used an initial estimate of length-based SPR from the LBSPR algorithm as a sort of proxy for what the current stock depletion rate is today. We are well aware that that SPR is not and depletion are two totally different metrics, and so again, this is being used in the absence of knowing concrete numbers around depletion. We then looked at four different catch scenarios in using the catch MSY algorithm to estimate current biomass. One is historical, which means we're using the historical catch from the sea around us combined with the modern catch in the modern years, 2016 to 2023. And we're assuming that there's no depletion, and that the fishery essentially started in 1950 and was depleted down to the current day's estimate for SPR as a proxy for depletion. The optimistic scenario is essentially is assumes that catch will remain the same at the same levels it is at today since 1950, but that the fishery started in 1950 with no depletion and then was depleted to its current state today. And then constant is just, again, constant catch as used, the constant catch of today's catch happening since 1950 to today, but with depletion being the same back in 1950 as it is today, so no change in depletion. And then the last scenario is pessimistic, which is a constant catch, but since 1970, and then a change in depletion over time to up to today's level of depletion. In reality, probably we're pretty certain that their fishing was happening prior to 1950 in this fishery. The extent or the amount of catch is not well known, so there's not really good information back in time. So this was sort of the best we could do to anchor our sort of catch time series. Now, I know at the mention of catch MSY, I know there's not video and I cannot see you, even though you can see me. I know probably most, if not all, of your faces look something like this, cringing at the mention of catch MSY, and I totally understand and I totally get it. And I also you have used this with a cringed face, and this is certainly an area of improvement that the work on which the workflow can be improved going forward. But for now, we used the Catch MSY algorithm just to generate estimates of current biomass and version biomass, and I'll address some of the strong assumptions and biases behind Catch MSY toward the end of the talk. Priors for the R and K parameters use samples from a uniform distribution for each species, and the model was run about 3,000 times per stock, and runs that didn't satisfy or did not sort of reproduce the catch dynamics appropriately enough, were rejected, and the remaining ones were kept. Um, for each stock, a geometric mean for the current biomass and virgin biomass were estimated, together with upper and lower confidence intervals. And if you combine all of those with all the sensitivity analyses around catch and depletion I just discussed, that gives you about approximately 12 different estimates of biomass per fish stock that's being assessed. For life history parameters, as I mentioned before, there are no empirical studies in this fishery. So what we did was we developed 5 different sort of data sets of life history that were all tested in the model and combined. So all these different scenarios and sensitivity tests I'm talking about, um, all permutations of these are combined in the analyses, and then the outputs from all of those are combined at the end, as I'll show soon, um, to determine estimates of stock status and such, with confidence intervals, such that what you can do is preserve that uncertainty, uncertainty in data and inputs, and uncertainty in modeling, in the sort of assumptions behind these different data limited modeling approaches, and then at the end be able to have an upper and lower bound to your estimates around stock status, as you'll see shortly. So for life history, we pulled life history parameters from FishBase and FishLife, where there were multiple entries for a given parameter. We took the average or the mean. We then calculated life history parameters from the data using the equations and assumptions you see here on the right side of the slide. So the von Bertalanffy equation and the weight-length relationship. We grabbed the A and B parameters from FishBase. That's the only place that those values can really be found. And so those parameters were used across all 5 of these life history data sets. We estimated natural mortality using a method in Duriel and Froese, which assumes this p parameter is 0.015 for many species of not only fish but terrestrial organisms, and by using the max age from fish life. And the reason why we use this algorithm or this equation to estimate natural mortality is because we estimated it using essentially all the equations I could find. And we ran the workflow with these different estimates of natural mortality. And for all the other methods, for most species and most stocks in most places, the estimate of natural mortality that was calculated by those methods was unrealistically high. So I'm talking estimates of M that are zero point 0.6, zero point 0.8, even 0.4 and zero point 0.5. You would essentially need a gang of sharks to show up and eat all of your target species to get natural mortality estimates that high. And so after combing the literature, and on the box here on the left shows some of the studies that were reviewed as a sort of sanity check to realize that those estimates were too high. We decided to use this approach, which gave much more realistic estimates of natural mortality in the ballpark that you would expect for the life history of the species being assessed and the health of the sort of the ecosystems and where the assessments are taking place. The von Bertalanffy growth K parameter was estimated using this equation from Froese and Binholin. And then L infinity was assumed to be equal to the largest size of fish that was sampled in the length data set from the catch. We know that, of course, that assumption is pretty strong, and there's probably larger fish that are out there. But that's the assumption we went with. And then the length of maturity was assumed to be 0.50 for snappers, 0.59 times the length of L infinity, 0.46 times L infinity for grouper, and half of L infinity for other species. And then the L opt parameter was assumed to be equal to 4/3 times the length at maturity, and all these sort of trends and assumptions come from this Newman et al. Study. Again, in the absence of actual empirical studies like we have for most of the stocks we assess here in the United States, these were some of the assumptions that we made to be able to develop life history data sets that we could sensitivity test around and use for this assessment. To estimate current fishing mortality, so current F estimations, we used 5 different algorithms or 5 different approaches. One is the LBSPR, length-based spawning potential ratio estimator that Adrian Hordek and others developed. The second is the Beverden and Holt instantaneous mortality estimator. The third is the Lime model that Merrill Rood and Jim Thorson developed. And I'll note that only 1 year of length data was used and catch was not integrated. We tried to integrate catch and some time series into the model, and we don't have, at the time, we did not have enough years of data, and the model would not converge essentially, or would produce highly unrealistic results. And so we really only used Lime to estimate current levels of fishing mortality and not in a more integrated assessment way. Where the hope is that as more years of data continue to be collected, that we can move to a more integrated assessment type framework. We also used good old-fashioned catch curve analysis to estimate F, and then something called I call solve the Baranov catch equation, where you essentially it's heavily reliant on catch, and so our assumptions about catch would have to be accurate for estimates from this approach to be accurate. But the idea is to essentially iteratively solve Baranov's catch equation to land on the fishing mortality rate that would reproduce the vector of catches at length or catches at age. For selectivity, we assumed selectivity was logistic, and it would be either for methods that for the fishing mortality estimation methods that would include an estimate of F. We told it to estimate it logistically. For those that don't, we estimated a logistic function to the ascending portion of the of the length frequency histogram, and assumed that represented selectivity essentially. We trialed dome-shaped selectivity in the workflow, but many of the fishing mortality estimation algorithms did not fare too well, and we ended up with unrealistically high estimates of F. When we all spoke to stakeholders, they also had very strong feelings that selectivity is not dome-shaped in this fishery, and that it's logistic. So we did not include in the results I share, and I show you that they do not include any runs with dome-shaped selectivity. Length bins were determined for each stock, so for each species in each of the fisheries management regions across Indonesia, and that was done. The best ideal length bin to use for each histogram was determined based on trialing different length bins and fitting a log normal function to the resulting histograms, and then selecting the log normal fit that had the lowest AIC or produced the best fit to that histogram. For some of them, where this failed and the model was not able to sort of converge and fit the a log normal distribution to these length frequency histograms, those were checked by eye and adjusted manually and to identify the best sort of breaks for that histogram. And that's important because we're using information from these histograms to figure out an estimate of fishing mortality. So it's important that that they reflect sort of the best representation of the sizes of animals that are caught in the fishery. So with our estimates of current biomass and virgin biomass from Catch MSY, those biomass estimates were then convert it to numbers at age vectors, sorry, based on by using the average weight of an individual fish in that population. And we figured that out given the weight length relationship and survival theory. So using total mortality for B current and natural mortality for biomass at virgin. And so through survival theory, we can figure out what the probability of survival is across age groups, and then use that to determine the fraction of the population that you would expect to have within each age group. And you can use that to calculate the average weight of one fish in your population. And then that average weight of one fish can be used to convert the biomass to numbers. And then those numbers can be distributed based on survivorship as into a vector of numbers at age. Now that we sort of moved, so by combining the output from catch MSY with the output from the fishing mortality estimation algorithms and um, getting to sort of a numbers at age world, we can now use the vector of numbers at age to forecast forward in a life table analysis type way what would happen with the population under different potential management scenarios. And so the forecasting just uses the same typical equations we're familiar with in fisheries for forecasting, where recruitment makes up the estimate of recruitment from a stock recruit relationship, which I'll talk about in a moment, becomes your numbers of age zero fish. Numbers that for any other age and year are estimated based on fishing and natural mortality and selectivity. And then your terminal year or your plus group is estimated in the way you see below. So we used a Beverton, we assumed a Beverton and Holt recruitment function. And I should say we did not fit any recruitment functions, obviously, during the assessment. And so what we did was we used recruitment as part of the forecasting part of the work to forecast forward the population status over time, and also to determine the fishery benchmarks over time, or not over time, but the fishery benchmarks under different states of population health. So like MSY, MEY, SPR 30%, etc. And I'll talk about that in a moment. But for the Beverton and Holt function, we estimated what the R0 parameter would be by using a Leslie matrix approach and iteratively trialing the sort of number of age zero fish and forecasting that population forward with only natural mortality until the numbers at age when that population reaches equilibrium matches the numbers at age that you got the current number, or sorry, the numbers at age you would get from by converting the biomass at virgin estimate from catch MSY to numbers at virgin and spreading those numbers out based on survivorship with only natural mortality. So once that was reached, once that number of recruits for R0 was reached, we determined that we had figured out what the R0 would be. And for steepness, we don't have good studies on steepness and such. So we sensitivity tested around the steepness parameter by using values of 0.7, 0.8, and 0.9 for each stock. And note that this increases the number of sensitivity analyses in the forecasting part and the biome and the benchmark estimation part of this work by a factor of 3, because you're sensitivity testing these 3 steepness parameters. Spawning stock biomass is estimated in the typical way by the numbers of mature, the weight of mature individuals, the sum of those across all age groups in a given year. Maturity at length followed a logistic function given the length of maturity at 50%. And selectivity followed a two-parameter logistic function. Note that both maturity and selectivity are expressed here in terms of length, but we developed age length keys to be able to switch back and forth between age and the age and the length world, so to speak. Okay, so 5 different management benchmarks were estimated by, again, iteratively forecasting out populations, the numbers at age vector, essentially, for each scenario and each stock to equilibrium until we reached the conditions that meet these benchmarks. So until the population stabilized with an SPR of 20%, or an SPR of 30%, or an SPR of 40%, or until the maximum sustainable yield catch was found, or the maximum profit was found for maximum economic yield. We also forecasted at business as usual, so at current fishing mortality rate, and that F equals 0, so that we would know how quickly populations could rebound if fishing were to be stopped completely, which is not realistic, of course. Um, and so the Indonesian government is, and so we estimated population benchmarks for each stock in these for these 5 benchmarks, but the Indonesian government is currently at the moment is using SPR 20% as their limit reference point. So the point at which they don't want biomass to fall below for any of these populations, and an SPR of 40% for their target reference point, which is the rate of fishing mortality that they do not want to exceed. For those species scenarios found to be below the limit reference point, a rebuilding time was estimated back to any of these 5 population benchmarks, and the amount of fishing mortality that would need to be reduced was also calculated. Note that the reduction in fishing mortality was not really shared in this presentation or in the manuscript that's in review, mostly for political reasons, because the reductions are quite that the model is estimating are quite large and highly unrealistic from a pragmatic perspective, while ensuring sort of socioeconomic considerations are met. And I'll talk a little bit more about that at the end. We then incorporated or built into the projection part of the workflow the upside economic model, which is talked about or discussed in Costello et al. In 2016. And that model allows you to estimate revenue, cost, and profit for each stock scenario, and for the years projecting forward. So for both current business, the current state of the fishery and projections forward in time. And that was estimated. These were estimated for all the management benchmarks and for current F projections. And then we used the NutriCast model, which is a fisheries nutrition estimation tool, and we built that into the workflow as well, the forecasting component, so that we could calculate essentially the nutritional composition of the catch under different potential management scenarios. And I'll show what those key nutritional markers were when we look at the results together. I realize I'm not providing equations for this or for the upside economic model, and that's just for brevity, and you all can go back to the manuscripts of those studies to look at the methodology. So these here are Kobe plots that are grouped by fish families. So and the multitude of points on these Kobe plots represent the different species within the fish family, and all combinations of all of the sensitivity scenarios and the 5 different fishing mortality estimation algorithms that were used as part of the sensitivity testing and the model ensemble approach. And the percentages in each of these quadrants shows you the number of runs that fell in each of these quadrants. So for snappers, you can see about 58% of the runs for snappers show that populations are in the U.S. what we would consider overfished, so below the limit reference point, and above the target reference point, where in the U.S. we would say overfishing is occurring. Same result for groupers, almost identical. And then emperors, very similar result. And then the grunts and other species that are a bit lower on lower in trophic level fared a bit better with less overfishing and overfished scenarios and species. Looking at this just a slightly different way, here you can see the dashed red line at 1, where values above that show healthy biomasses for these species, each of these species on the x-axis, and values below that show unhealthy biomasses found. And this is for all the fishing management areas combined across the entire country of Indonesia. You can see that there's the uncertainty is captured here in these box and whisker plots, which is nice. So across all uh, the sort of ensemble of models and scenarios. And you can see that some species are doing okay and others require rebuilding. Looking at it spatially across fisheries management areas, a lot, at least half, are essentially below the limit reference point, so have biomasses that are too low, and that's can be disconcerting if these results are accurate. And then for the target reference point, so for overfishing, you'll see here's the line at 1, that most species fall mostly above that. So overfishing is occurring for most scenarios in most species, which is not ideal, again, for all fishery management areas combined. And then looking at that spatially, it shows essentially the same thing, that in most fisheries management areas, at least, about approximately 3/4 of the species have fishing mortality rates that are above the target reference point. Or again, in the US, we would say are experiencing overfishing. Length-based SPR estimates are here, and most of them are below. I have this line here at the 40% SPR, and so most of them or a lot of them are below, or a lot of the bars, a lot of the runs were found to be below that line. And then for rebuilding times, and again, I've grouped things here again by fish family, just because it's easier than showing results for a whole bunch of species. And you'll see, as expected, that if you want to rebuild, for example, to maximum economic yield, that will take a certain amount of time, on average about 10-ish, 11 years for emperors, groupers about 14 or 15. Snappers about 10 years, etc. If you want to rebuild to SPR 30%, you're looking at about 10 years for snapper, 5 or 6 for other species, 10 years for grouper, and 10 years for emperors. And so looking at the results like this, fishery managers can then make informed decisions about, one, what reference points they want to use in terms of their target limit reference points, and two, what it would take to rebuild, what the sort of trade-offs are, right, of rebuilding. If I manage at a low SPR, at SPR 20%, it will take a lot longer to rebuild things, but you will have a less of a reduction in fishing effort that needs to happen. Whereas managing at SPR 40%, you will take a lot shorter to rebuild, but you'll have to reduce your fishing effort more substantially to pull that off. When looking at sort of differences in catch across these different scenarios, so current is sort of business as usual, continuing on with current fishing mortality, with the current fishing mortality rate. And then if you were to manage at SPR 20%, 30%, 40%, MSY and MEY, and you'll see that the species compositions of the catch don't change very much. So the catch remains dominated by these two snapper species. This dark green is Lujanus malabaricus, and the light green is Prismapoides multidens, which are the two commonly the most marketable snapper species that are caught and sold both in country and exported to other countries, including here in the United States. And essentially, the yields vary a bit. These are yields that you would expect once you kind of rebuild and reach that equilibrium state of the fishery at these different reference points. And so there are not huge differences in yields, but some difference, and there's not much difference in species composition. In terms of profit, there is a huge difference once you start managing this fishery a bit better. So at the moment, a lot of they're losing a lot of money from Lujanus malabaricus, which is not being managed as sustainably as it otherwise could. And so getting that species to sort of recover and rebuild will help recover your profits for this fishery, regardless of which management benchmark you choose to use. Nutritionally, I was surprised. So, given that this is a multi-species fishery, I expected more variability as fish populations across these 43, 45 species rebuild. I expected a bit more variability both in catch and in the nutrient content of the catch. So, in catch, meaning in the species composition of the catch and in the nutritional composition. But the nutritional composition is following the species composition of the catch, so it makes sense that the nutritional profile will not change very much from one management benchmark to the next. And in a way, that's kind of reassuring from a food security perspective as well. So I'll go over some of the assumptions and limitations. There are of course more, and the manuscript is currently in peer review with Nature Communications, so you can read in more detail about this once it's published. I'll send it around to folks who I think may be of interest, or if you have insomnia issues, you can also use it. It will also serve quite well to help you get to sleep at night. But anyway, some of the strong assumptions are that the spatial fishing location data suggests the potential for local depletion. And so fishers, when you look at where they're fishing, they're returning to the same places time and time again. And that could lead to local depletion, which could cause overly pessimistic stock status results from these analyses. I believe that for some of these species, there are some issues, but I don't quite believe the magnitude of the severity of the stock status that the analysis is suggesting, both due to many long conversations with stakeholders and such, but also due to the fact that they keep landing approximately 80,000 metric tons of these fish year after year. And while there might be, effects that are sort of keeping that number artificially high despite depletion occurring, um, it's still interesting that they're still able year after year to harvest that quite a large amount of fish. Also, each fishing mortality estimation algorithm has its own strong assumptions, strengths, and weaknesses. There are several papers out that address that. Landings extrapolation has quite a bit of uncertainty, and there's a lot of uncertainty around the catch. And we know that catch does not always track trends in abundance, and so its use in catch MSY could be could produce quite erroneous estimates of biomass if catch and biomass are not correlated, right? The catch MSY algorithm has a ton of issues. I totally get that, and leans on some pretty heavy assumptions. It's been found to underperform with lightly exploited stocks and perform a bit more accurately with more heavily exploited stocks. And depending on life history, how long lived that species is. And then the growth rate and carrying capacity estimates tend to be underestimated and or overestimated, growth rate tends to be underestimated, and carrying capacity, overestimated from Catch MSY. And that overestimation of K, since we're using the estimate of K to know what the biomass at virgin was and the numbers at age at virgin were, any biases coming out of Catch MSY in the estimates of carrying capacity would be propagated through the system throughout the whole workflow and could manifest as overly pessimistic stock status determination relative to reference points. And so, again, that's just some of the assumptions. You can read in more detail about them when the manuscript's out. And so, in summary, applying a combination of all these different data limited approaches with all these sensitivity scenarios and such was really useful because it produced a range of population realizations for each stock, or sort of states of nature, if you would, for each stock, which when combined, we were able to then estimate, what I'll show in a moment, sort of what, where things are relative to each reference point, together with the upper and lower confidence limits of that stock status estimate. And so, given uncertainty, scientific advice from the results can still be used to understand stock health and guide policy decision making, while acknowledging the uncertainty in both process modeling processes and in data. And so, as an example to show you that despite wide uncertainty, these results can be useful, this is just a short snippet of one of the benchmark tables, which show for some of the species. It's cut off here, so I'm only showing some just to give you an idea. And these are ranges of current biomass divided by the biomass at SPR 20% for all of the sensitivity scenarios, all the combinations of sensitivity scenarios and fishing mortality estimation algorithms. And I've color coded this green for those where overfish, those where the stock is not below the limit reference point, so where things are clearly not overfished because the lower and upper confidence limits are well above 1. Sort of other scenarios that are straddling, where some scenarios are suggesting things may be, the species may be below the limit reference point, and others saying, oh, it's above. And then in red, where all the scenarios are saying, oh yeah, the results for this species are below the limit reference point and biomass amounts are too low. And so, in summary, many snapper, grouper, and emperor species and their respective scenarios that were run are below their limit or target reference points, and so rebuilding is required. Not as many species at lower trophic levels, generally speaking, are below their limit or target reference points, but there's still quite a number of them that are. Reductions in fishing effort to rebuild stocks need to occur in very small increments over a long period of time. And the reasons for this is because Indonesia is the second largest. Indonesia has the second largest capture of wild, or landings of wild capture fisheries, second only to China, which has the first largest. It is the country that catches the most from wild capture fisheries. And so commercial fishing is very, very important to local, regional, and national economy across the country of Indonesia. And so, given this reliance on seafood production at large scales for export and sale, and at smaller scales for food security and local use for and local consumption, the sort of stronger reductions in fishing effort that the model wants to suggest are not realistic. And so a better approach would be very small sort of increments over long periods of time. And I would share, I'm clearly not Indonesian, and so I don't have a dog in this fight, so to speak. It's not for me to come in and say, oh yeah, I think the government should manage their fisheries in this way or that way, or manage them at all. I don't pay taxes in Indonesia. I don't live there, and I'm not Indonesian. I'm simply saying, oh yeah, here are some scientific results. Here are all the assumptions behind those results, and allowing the managers and experts to ask me questions about the analysis, but then have them have their own conversations, and make their own decisions about how they want to manage this fishery. Rebuilding could make the fishery profitable, but cautions advised to avoid issues around choke species. I know I'm running out of time, so quickly, these similar trends are seen in several other studies that have been done over the past 5 to 8 years that are sort of listed here, either nationally or in different locations. So keep that in mind, that these results are not in isolation, that other studies are finding similar trends. And using the model workflow, we're hoping to explore several different policies in close coordination with the national government. So the national government is charged with establishing catch limits at the moment, but is having trouble figuring out how to do that in a science-based way. So we're the next sort of steps of this research would be to explore using the workflow for that potentially also looking at what phased reductions in fishing effort would do over time to projections. Um, Also important to look at size limits and such that can be looked at in the workflow and in the forecasting. And then ultimately looking more into fisher behavior and spatial fishing patterns using the fishing location data to assist with policy decision making. Some of this work has been started through the work through structured interviews and surveys several years ago. And we're hoping that this will inform fishery management plans, and ultimately, we'd like to explore climate change implications as well. In addition to this quantitative work, I've been doing a bit of what I call fisheries diplomacy. So I received a small grant from the U.S. Embassy in Jakarta to make some trips to Indonesia and work with local national scientists at the national and the regional levels to help essentially improve their knowledge of technical stock assessment techniques and decision theory around fisheries management. All these folks are extremely bright, and most of them have PhD terminal degrees. However, most have not had the great privilege of going to the schools that have heavy fishery programs, and so there are some knowledge gaps that can be filled, and I'm helping try to fill those gaps with the idea of ultimately getting the white guy, meaning me, out of the way, so that and handing them over my workflow and giving them the opportunity to trial and use other models, things like Java, etc., to assess their fisheries. Now that since 2016, there's much more data available and different types of data available to evaluate these fisheries. So we had one workshop last year and three this year. I was there in May, and I'll be back in October and in December for additional workshops. And lastly, as a shameless plug, I am guest editing a special issue on the dynamics of coral reef fish. I know it says the deadline was August 10th, which it was and has passed, but we're still open to receiving submissions. If you're interested, please send me an email. Here's my email address, and let me know that you'd like to submit something. I can get publication charges waived. Everything will be open access, and will be compiled into this special issue. And we've got a handful of submissions already. I'm just trying to get several more. And thank you all for your time and for joining today.
Awesome. Thank you so much for your presentation. That was really great. And just checking to make sure. It doesn't look like any questions have come in. Looks like you sated everyone's curiosity for the hour.
I don't know about
Uh,
that. I doubt that.
uh, but thank you again for sharing your work with us today. And thank you, Bai, for organizing this event.
Yeah, thank you
Awesome.
all for attending and for having me. I appreciate it.
Yeah, thank you. And audience, thank you for being here today. Please join us next month for our next National Stock Assessment Science Seminar. Take care and enjoy the rest of your day.